In the previous classes, we had looked at the working with the hyperbolic model and how we can perform some numerical analysis, and we have also seen how to do the stress correction to bring the stress state back to the yield surface. And in today's class, let us look at some more practical problems, that is how to obtain limit solutions using finite element approach. I will focus only on the bearing capacity and lateral earth pressures, because for which we have theoretical solutions. And the brief outline is determination of bearing capacity factors, and then determination of the active and the passive earth pressures, and we will see how to incorporate the effect of different types of wall movement, that is lateral translation, that is the that is corresponding to Rankin's active earth pressure theory or passive earth pressure theory, where he assumed that the entire wall deforms laterally either away from the soil or into the soil, or we can consider rotation about the bottom and rotation about the top. Okay. And then we will also look at the influence of K naught, that is the initial earth pressure state, on the magnitudes of deformation that we require for achieving our active and passive limit states. And in all these, I will demonstrate the use of the GeoFM program that is going to come as part of this course, that you can use for doing all these analysis. And before we go in, I just want to highlight some data that we give for the GeoFM program. This is called as the master control data. This comes on the second line. The first line is the title of the work that you are doing, and this is the second line. It has very important data, and number of nodal points is the total number of nodes that you have in the mesh, and then the number of element types, and then the analysis type 0 and 1. 0 is for linear elastic analysis and 1 for nonlinear analysis, and nonlinear including the elastic plastic and all these things. This particular index is important, because if you place it as 0, then the program will not calculate the reaction forces, and it will assume that you are satisfying the equilibrium at all the times, and it will not calculate the out of balance forces and the norm of out of balance forces and so on. And if you give it as 1, then the program will calculate the reaction forces, and this value is also automatically chosen by the program in case you have any incremental construction or execution. This has to be 1, because you require your B transpose sigma or N transpose B vectors, and then if any of your materials has elastic plastic constitutive matrix, that also requires. And then IBFRC is for considering the gravity forces. If it is 0, you do not consider any gravity forces, and if it is 1, then it considers the gravity forces. And iplot is to create a post processor file in the binary format. 0 means it will not create the file, and 1 means it will create a file, and you need to give a name for this file. ICNST is also very important parameter that we will see in the next class, a demonstration of how to do the incremental construction and incremental execution. 0 means the entire mesh is constructed at one stretch, and 1 means the mesh is constructed incrementally, that is to simulate incremental construction. And then NR form is actually, it is a very important parameter that tells the program how to update the stiffness matrix. If you give it as 1, then the stiffness matrix is updated at every iteration. Updated means it has to go through the calculation B transpose dB and then assemble it, and then even the triangulation. Then plus n means the matrix is updated at every n, 2nth and so on. Like if you give it as 10, then the stiffness matrix is updated at the end of 10th iteration, 20th iteration and so on. And then minus n means it gets updated only once within a load step. At say if you give it as minus 1, then the stiffness matrix is updated at the first iteration in every load step. So load step 1, it will get updated at the first iteration. Load step 2 till once again get updated at the first load step. And you can simulate the initial stress analysis where we do not update the stiffness matrix by just simply giving this value as some very large value, say some 10,000 or 100,000. Then this condition of plus n will never happen, because you are not going to have that many number of iterations. And in all these things you may need to run the program repeatedly. So if this mode x is the mode of program execution, 0 means it is only a data check run. It will the program will run through and tell you whether the entire data is good or bad. Like if some data is inconsistent, then it will prompt you 1 for initial analysis. And as I mentioned earlier, all these finite element programs, they can take a very long CPU time. Sometimes the CPU time could be even 1 week. And if you want to examine the results say every day, you can run the program up to certain stage, stop it, examine the results and then restart. And the mode x of 2 means you can restart the program from where you stopped previously. And especially when we are doing the incremental construction or the change of boundary type, like sometimes we change the boundary from a load control boundary to a displacement control boundary. In that case also this option becomes quite useful. And let us say you apply the k naught with a very large value, like k naught of 3, means it will the program will apply the self weight with a Poisson's dummy Poisson's ratio of k naught by 1 plus k naught, that is 0.75. And then at the end of the analysis, anyway the program will reset all the displacements and then the strains to 0. You will generate the required earth pressure state. Say the vertical pressure will be gamma z and the lateral pressure will be k naught times gamma z. And in this case, because your Poisson's ratio is beyond your elastic limits of -1 to 0.5, that Poisson's ratio needs to be reset before you do the actual analysis. So in that case, what we do is we apply the k naught with mode x of 1 and then restart the analysis with a mode x of 2 later. Okay, that's one way of overcoming this problem of incompatible Poisson's ratio. That also I will demonstrate. And in this lecture, I am going to follow this paper that was published long time back by Professor Griffiths. He is now at the University of Colorado. He published a paper on computation of bearing capacity factors using finite elements. And you can, if you are interested, you can refer to this paper. And all of us know the Terzaghi's bearing capacity equation. The Q and U is C and C plus Q and Q plus 1/2 gamma B n gamma, where NC, NQ and N gamma are the bearing capacity factors, and which are related to the friction angle. And there are different theories that describe how to determine these NC and Q and N gamma in terms of the friction angle phi. Starting from Terzaghi, in 1943, and Meyerhoff, in a series of papers he published number of them to estimate these bearing capacity factors. And in between we have several other theories by Hansen and then Balla and so on. And then we have the Wessex theory in 1973. In fact, our IS 6403 is based on the Wessex theory, and Wessex also has proposed bearing capacity factors NC, NQ and N gamma, and then also the shape factors for representing the shape of the footing and so on. And in this lecture I am going to only demonstrate the bearing capacity determination for a strip footing and for a circular footing. And these factors NC, NQ and N gamma they can be determined through systematic finite element analysis as described by Griffiths, and I am going to describe now for all of you. And this finite element analysis becomes necessary if you want to analyze for a layered soil profile, or let us say your soil profile is highly complicated. You have inclined soil layers and then some joints and so on, and you want to know what is the effect of any footing constructed on such a soil. You cannot use any of the existing theories, because all these theories by Terzaghi, Meyerhoff, Wessex and so on, they only assumed homogeneous soil conditions, and they assumed that the boundary is far away. And but in some cases your hard strata may be at a shallow depth compared to your foundation width. In that case your actual bearing capacity may be much more than what these theories predict. Let me just highlight my laser pointer. Okay. So, these bearing capacity theories, they assume homogeneous soil, and then the boundary at a large distance from the footing. But for other cases we need to use some other methods like finite element analysis. Well, let us first look at the factor NC. We can perform analysis by giving both C and phi properties to the soil, and we can consider a surface footing such that our gamma df, that is the Q, is 0 and the effect of NQ factor is eliminated, and we can set the unit weight gamma to 0 so that your N gamma effect is eliminated, and then we can estimate NC as the QU, that is the numerically predicted ultimate bearing pressure, that divided by C will be your NC. Just to highlight, so if you see this equation C and C plus Q and Q plus 1/2 gamma B N gamma, the Q is the overburden pressure at the footing level, that is gamma df or gamma prime df, and if you take the footing at the surface, your Q is 0, and if you give N gamma of 0, then the N gamma effect is not there, and your bearing capacity is only because of this C and C. So, this is what we are going to do, and in all these cases, if you have a symmetric loading, we consider only half the footing by considering the symmetry boundary conditions. So, at the center of the footing or at the mid section, along the mid section, your lateral deformations are 0, because you have a uniform pressure and it is symmetric. So, this condition that all the lateral deformations are 0 along the mid section, that itself is our symmetry boundary condition, and by doing that we can consider only half the footing. Okay. And we can determine NQ by performing the analysis by setting a C to 0 such that the effect of NC factor is eliminated, and we consider surface footing, but then apply some overburden pressure the Q on the surface on both the sides of the footing, and then we set the gamma, the unit weight of the soil, to 0, so that the effect of N gamma is eliminated. And then once you get your QU, that is the numerically predicted ultimate bearing pressure, NQ is QU by Q, where Q is the applied pressure and Q is the bearing pressure that we determined from the analysis. And once again we consider only half the footing by considering the symmetry. Then the this is NQ, and then N gamma. Okay, I am sorry about that. I think I cut and pasted, but okay, for determining the N gamma, we can set C of 0, so that the NC factor is eliminated, and then we place the footing at the surface so that our Q is 0 and our NQ effect is also eliminated, and we can set the unit weight of the soil to gamma and then perform the bearing capacity analysis, and our N gamma is QU by Q. So, separately we can determine NC, NQ and N gamma, and then we can superimpose them, or you can also do that through the finite element analysis. We will see that we can get the bearing capacity because of all the contributions, because of the cohesive strength and because of the overburden pressure, and then because of the unit weight of the soil. And we can actually have different variations of the type of footings. Let us say we have a smooth and rigid footing under symmetric loading, and the rigidity of the footing we can simulate by applying equal vertical settlement to all the nodes on the footing, so that the rigidity of the footing is simulated, and the uniform settlement is representative of the rigid nature of the footing. By rigid, what we mean is the settlement is uniform over the entire footing, provided your loading is symmetric. If you have an unsymmetric loading, that you will not have it, that we will see later. And then we allow the nodes on the footing to move freely in both vertical and lateral directions to simulate the smooth interface between the footing and then the soil. And we consider only half width of the footing to enforce the symmetry by enforcing the symmetry boundary conditions. And then we can also have a rough rigid footing, wherein our footing is perfectly bonded with the soil, and once again the rigidity of the footing is simulated by applying equal vertical displacements to all the nodes on the footing, and then we fix the nodes on the footing in the horizontal direction, so that the nodes are forced to move only in the vertical direction, and this is to simulate the rough interface between the footing and then the soil. And once again we consider only half width of the footing by enforcing symmetry boundary conditions. And sometimes we may have a eccentrically loaded footing. Let us say you have a strip footing with an eccentric loading, and let us say that our footing is smooth, and if you have this type of loading, we do not really know how the settlements change. So, it is we cannot really apply any displacements because we do not know how much displacement we need to apply and in what proportion. So, we can simulate this in an indirect manner. We can simulate the footing through either a continuum element or a beam element. Usually we use a beam element because it is more easy to control the modulus. You can control the Young's modulus, and then the moment of inertia, and then the section, and then we can apply the loading eccentrically, and we provide a interface between the footing and then the soil, so that we can simulate the slip. We can give the exact properties of the interface between the footing and then the soil, and if the footing is perfectly smooth, what we do is we give the shear modulus of the interface element to, we set it to a very small value, not exactly 0, but some small value, so that the soil nodes can move freely laterally. And here we are forced to consider the full width of the footing because there is no symmetry, and so we need to consider the full width, and then the soil on both to the right hand side and the left hand side, and we can apply the load. And in the GeoFM program, there is an option for using the constraints. We can relate the displacements along the footing through some linear equation, so that we can simulate the rigidity of the footing. But I do not suggest using that because that will complicate the analysis, and that will actually spoil the banded nature of the stiffness matrix, and then you end up spending lot of time in doing the computations. Only for small problems you can do the constraint option, but for a large problem you better use a rigid element like either a beam element or a continuum. Then if you have a rough rigid footing with eccentric loading, we do not provide any interface element. We directly connect the beam element with the soil element, so that the soil nodes will move along with the beam, and this is to simulate the roughness of the interface between the footing and then the soil. And here you see the deformation of the pattern of a flexible strip footing. Actually it's a smooth footing, and if it is a flexible footing, we assume that the pressure is constant all through the footing, and what we do is we apply equal pressure. And here I want to illustrate, we are considering only half the width of the footing, and you see the roller boundary conditions along the mid section of the footing. This is to represent the symmetry in the response, and on the right hand side also we have provided roller boundary conditions, so that you do not generate some spurious shear stresses. So if you fix all these nodes, because of this applied loading, the soil naturally would like to settle down or deform, or might instead of settling down, it might even heave up. And if you fix these boundaries, there might be some spurious shear stresses that could affect our results. Then at the bottom, we assume that we have a rough rigid surface. So all the displacements on these nodes are fixed. So that is shown by a hinge. This is a roller, typical roller at all these, and the elements that are used are 8 node quadrilaterals, and this particular soil is a clay soil with a C of 25 and phi of 0, and you see, you can actually see the pattern of the circular slip surface. If your phi is 0, your slip surface will be more like a circular slip surface, and this is your flow vector. These are the flow vectors, and this is your deformation pattern. The yellow line is your original mesh, and then this black line is the deformed mesh. And this is the rigid footing. When we have a rigid footing, we apply equal vertical displacements. There are 3 nodes on this surface, so we have applied equal vertical displacement, and because it is a smooth footing, we are allowing these nodes to deform laterally. So, this particular node what was there has deformed to this position, because we are allowing the nodes to move freely. As you are compressing in one direction, the material will expand in the other direction. That is what we see here. In fact, through these vectors you can see this particular node, it is not only moving vertically but also moving laterally. So, this is the resultant direction, and all these vectors, they represent the direction of the displacement, and they are all scaled vectors. So, the maximum length is representing some length that I think I did not plot here, but when we see the post processor, I will show you that. And these are the flow vectors for a rigid footing, and you can see under flexible footing you have one deformation pattern, and then under a rigid footing you have a different pattern, because actually when we are deforming the soil, this is the deformation pattern. We get a similar pattern, but the effect of load is distributed for a longer distance, because the pressure, once you apply the pressure, it has to disperse. But if you apply displacement, the effect may not disperse deep, because if the soil elements here they enter the plasticity, the effect of that is not seen here. So, that is why you see most of the deformations are confined to only the soil around the footing, and just for the purpose of quick calculations, I have used a very coarse mesh, and the results that you get with this may not be very accurate. And since I am going to run this program in front of you, and I want this to run quickly, I used only a small mesh, but we might get slightly different results if you take a much finer mesh. So, you see the effect of load control analysis. With load control, once you apply the pressure on the surface, it has to naturally spread to a longer depth and width, because the pressure has to disperse. Whereas with the displacements, we represent a better distribution, because if the soil elements around the footing fail, then you get a localized slip surface. That is what we see here. And these are the pressure settlement graphs for a strip footing and a circular footing. And for a strip footing, it is predicting about 150 kPa, and so your NC factor for a strip footing is about 6. Actually, as per our Terzaghi's theory, it is 5.7, whereas as per Vesik's theory it is 5.14. So, it is not bad. Like, actually we have used a very coarse mesh, but still we got value NC very close to the to about 5.7. And we also know that circular footing will have a higher bearing capacity by about 30%. So, if you see here, your this is the bearing pressure graph for a circular footing for the same properties of C of 25 and phi of 0. It has reached an ultimate pressure of about 210. So, your NC factor is more, because and that shape factor of about 1.3 for circular footing is because of the higher bearing pressure that you get because of this three-dimensional load distribution. And this is actually I will show you this this graph. We can actually, within a mesh, we can choose any line and plot how the pressures change. That I will demonstrate when we go to the post processor. and this is the rigid footing. So actually what I had shown is for a actually this is for a, this is for a rigid footing also, and this is for a rigid smooth footing, and this is for a rough rigid footing. Actually these three nodes, they correspond to the footing, and we have applied equal vertical displacement to all these three nodes, and then we constrained all these three nodes from moving in the horizontal direction, and that is what we see here. It is actually, we see the roller here, so that means that this particular node will move only in the vertical direction and not in the lateral direction. That is why you see this this vector is going down, and the effect of smooth and rough footings. This is the rough footing and this is the smooth footing, and our Terzaghi's theory and Meyerhof, they all consider a rough rigid footing. So the finite element results that we get with roughness, they are closer to the reality, that is our bearing capacity theories, and with smooth footings you get a slightly lesser pressure. And before we go into the finite element demonstrations, let us also look at the lateral earth pressures, and we will simulate only the Rankine's values, both active and passive, and Rankine has assumed the lateral translational type deformations, and we can simulate this by placing some depth of soil, and then we place the rollers all along the horizontal surface, so that we have only a smooth lateral deformation, and then we take the boundary at a far off place, and then place rollers on them, okay. And we can apply equal horizontal displacements along this surface, and if you apply these displacements away from the soil, we are going to generate active pressures, and if you apply these displacements into the soil, we develop passive pressures, and the smooth rollers are for simulating the smooth boundaries. And from our earth pressure theory, we know that if you deform the soil away from the if you deform the wall away from the soil, you develop some active pressure state, and if you push the wall into the soil, you develop passive earth pressure state, and the magnitudes of deformation that we require for active state are very small, whereas for passive pressure they are very large, of the order of about 1 to 5% depending on the type of soil. And when we simulate this through finite element analysis, we can estimate the lateral pressure constant K as the P is the sum total of the reaction forces on the nodes where we applied the deformations. The sum total divided by 1/2 gamma h square will give you the K. Okay, and this is a simple thing, because in all these programs there will be a post processor that can that will let you do these calculations very easily, and typical deformations for generating the active earth pressure state are about 0.2 to 0.3% of the wall height, very small deformations, whereas passive state is achieved at a very large deformation, 1 to 5% depending on the friction angle and so on. And also even the K naught value could affect the required deformations. And here I am showing you the variation of K with lateral translational deformation for 3 different cases, and all these cases they correspond to a phi of 35 degrees and a C of 0, and the Ka is 0.271, and this is the result. This green line is the result with a K naught of 0.5, and this red line is with a K naught of 1, and in both the cases we see that with the K naught of 0.5 we reach this limit state of 0.271, the K of 0.271 at a lateral deformation of about 0.04% of the wall height, whereas when K naught is 1, you require much larger deformations of the order of about 0.09. And if we take K naught of 2, even after about 0.16%, we have not still reached the limit state. It is still far away from the limit state. But if you continue further, then we might reach the limit state at a very large lateral deformation. And we see that all the deformations that we are dealing with for the active state are very small, about 0.1%, 0.05%. That also depends on the Young's modulus and then the K naught. And this is the plot for passive pressure, and for two different friction angles, phi of 30 degrees and 35 degrees. And when phi is 30 degrees, the Kp is 3, and when phi is 35 degrees, Kp is 3.69, and the initial starting point K naught is 1 for both the cases, and this red line is for friction angle of 30 degrees. It has reached the limit state of K of 3 at a deformation of about 2.6%, whereas when friction angle is 35 degrees, we require about 3.7%, because with a higher friction angle we generate more pressure, so that requires more deformation. And here we see the effect of the K naught. This green line is corresponding to 30 degrees friction angle, and this red line is also corresponding to 30 degrees friction angle. With a K naught of 1, we have seen earlier that you require almost 2.6% of the wall height deformation to reach the Ka state. But if your K naught is 2, initial K naught itself is high, closer to 3, you require only 1.4% wall deformation, because already the K naught of 3. So you might think, if what if K naught is 3, then initial itself the soil will be in passive state, and with further increase of the lateral deformations, the pressure state will not change. It will remain at a K naught of 3, and this is for 35 degrees. With a K naught of 1, we require about 3.7% wall deformation. Okay. So these are some limit solutions that we can easily derive based on our finite element analysis. And let me now open the finite element program and the data files and show you what exactly we are going to do. Okay, this is the end of my PowerPoint presentation, but we will come back to here. Okay. See, this GeoFEM is the program that you will get. This is the geotechnical finite element modeling, and this is only a 2D program, and there is another version, GeoFEM 3D, and if you are comfortable using it, I don't mind sharing that program also for 3-dimensional analysis. And let me just show you one. This is the data file for generating active pressure state, and I have taken a very small mesh of 117 nodes. And here, when you give the material point data, there is the last value that you give is the K naught. So, this is the k naught of 2, okay, and then we are going to demonstrate the active pressure case, and let me just run this for one case. Oops. And I will demonstrate the run with 1 mod x of 1, that is we are going to run with a k naught of 2, and that will give us a Poisson's ratio of 2 by 3, that is more than 0.5. Okay. And so, let me initially the lateral deformations are 0, that is what the boundary condition value we are prescribing, the negative 0.01, that is about 1% of the 0.3% of the wall height, and this is an active deformation, it is moving away from the soil. Okay. So, let me run this. So, I am just generating a result, and this is the result that we have. Let me zoom in. So, this particular one was this stress condition is 2, that is the plane strain case, and our friction angle is internal friction angle is 35 degrees, and dilation angle is neglected 0, and then the earth pressure constant is 2. Okay. So, if you look at at the end of the first stage, all the displacements are set to 0. I have not printed all the displacements, but you can see here see the displacement x and y, everything is 0, and here if you see sigma x is minus 111.55, whereas sigma yy is 55.77, and this multiplied by 2 is your 111.55, and we can actually see this in the, let me open the so this is our mesh, and we can display the boundary conditions. These are the boundary conditions, and then let me show you. Okay. So, these are the vectors of the stresses, the principal stresses. So, you see the length of this horizontal vector is long compared to the vertical one, is almost double, because our k naught is 2, and you see the maximum compression stress is 111.5, and this tension, it is printing, but there is no tension in this in the soil, because it is under k naught conditions, but then this is a spurious value that it has to show something, and our displacements are 0, because we have reset all the displacements to 0. Okay. And now let me do this. Let me rerun, restart the program with a mod x of 2, and let me think we may need about let me just run for about 0.05 deformation, and this will take some time, and I am using an NR form of 1000, so that the stiffness matrix is not reformulated, and the analysis will go very fast. So, that is what we see here, because the stiffness matrix is not updated. Okay. So, it's actually on my laptop it will run much faster, but since I am running on a vacuum tablet, it's not so fast. So, I have totally 1200 steps. So, it will take some time, maybe another 1 minute. It's 700, 800. Yes, it will run fast. 900. It's almost there. Yeah, 1200. Okay, right. It is finished. So now let me show you active heads. Okay, we need to first set the load step, at least once you have to do, so that you will be able to generate the or show the mesh and so on. And let me just set the current load step to the last value, 1200. Okay, and then this is the deformed mesh, and let me just magnify the deformations a bit. Okay, see this the yellow line is the original one, the black one is the deformed mesh, and we can see the vectors. Okay, so we have applied horizontal deformations, equal horizontal deformations to all the nodes on this boundary. Okay, and let us look at one of the stress components. See these are all the integration points. I am going to select one this point, and it is going to plot the lateral earth pressures at that particular point. And as the wall is deforming, the pressure has reduced. Initially it is about 111, but as the wall is deforming, this is on the x axis you have the epsilon x, and it is a tensile strain because we are extending, and then at some point it has reached the constant stress. We do not know what is the K, but because this divided by sigma y will be your K. And if you look at this is the sigma x, and I am going to plot sigma y, and the sigma y should remain constant. Okay, so that is what we see here. The sigma y is remaining constant at gamma z, and that is although we are applying lateral strain, the sigma z is remaining constant. Okay, and I want to demonstrate, I want to show you one feature of the program. Let us say we have plotted this, and we can actually generate a PDF file of this deformation. Like you can go to print, and this particular program is Windows compatible. So if you connect any printer to your computer, you can print it, or you can generate the PDF file. Oh God, I think I am not sure whether. Okay, let me try PDF annotator. Okay, and then it will be sent to a PDF file. I am not sure where it is. I think it is still working. Yeah, okay. Here is the PDF file of your deformed plot. Okay, and you can also export it as a meta file. Export meta file, and then you can give some file name. So all these are meta files that are created. Later you can import them into MS Word or into PowerPoint for your for preparing your slides. Okay, you can give any name that you want. Okay, and you can save it. Okay, and so on. You can do all these things, and there is another feature that helps us in quickly summarizing the results. This is you press on this pen, and then you can create a summary file with only the selected results. See, we have done the analysis, and we want to know how the earth pressure constant is changing with the lateral deformations, and here it is prompting you to all the data that you generate through this will be saved in a file, and let's say I want to save it as an active, and say translation dot dat, and then the search radius. See, the program will prompt you to select some nodes and select some displacements, and when you float the cursor, you may not be able to exactly match the node coordinates. So within a tolerance of 0.1, it will search the nearest node. Okay, so that is the search radius 0.1. Okay, I am saying yes, and then the width of the footing. This option is actually you can enter 90, 1/2 gamma h square. Our gamma is 20, and the height of the wall is 3. That is 1/2 20 times 9 is 90. So if you give this as 90, and then the direction for the reaction forces, we are applying the displacements in the horizontal direction, that is the direction 1. So you choose it as 1, and then it will sum up all the reaction forces at different steps, and then divide by 90 to calculate our earth pressure constant. Okay, so okay, and then we are interested in knowing how much was the deformation. So I'm floating the cursor, and then sticking, and if you have any interface, at the interface you could have possibly three nodes with the same coordinates. So the program is asking which of these nodes you want: node 1, second node, first node, second node, third node. I am just saying 1. Okay, and then the degree of freedom of that particular displacement. We are interested in the horizontal deformation, so the degree of freedom is 1. Okay, and then is asking whether you want to save any other nodal point data, and let us say we select another node. Okay, and once again 1, and then let us say we want to store the vertical deformation. Okay, and so I am saying it as 2. Okay, and then we can say no. Okay, and then there is another option for contour plotting. I am not so if you press this, you can give some file name, and then it will ask you what is the range of the contours that you want to generate, and then what is the x and y axis range, and then let us say it is giving a minimum x of 0.21. let us give it as 0.2, and maximum x is 19, let's say 20, and minimum y is 0.2, and say I give maximum y as 3, and then number of grid points, and then actually this is this program is going to generate the data in the XYZ format. X and y are the nodal coordinates, and z is the contour value, and it can interpolate by providing a grid of values. Let's say along the x axis I want 20 points, and then along the y axis I need 10 points. Okay, you say yes, and actually it is and then the contour lines, let's say 10. Okay, and oops, I think sorry, I think this is not working. I don't know, maybe I don't know how to use this. I'm just giving contour values. So let's open our file that we have generated. This is the summary file that we have generated. Let me zoom it a bit. See, these are the number of load steps that we have run up to 1200 steps, and then our initial K0 is close to 2, so it is 1.98, and our lateral deformation at node 1 at x coordinate of 0 and y of 3. This is the x direction displacement, and then at some other point we have selected y direction displacement. Then these are the displacements with the load step. Okay, we have applied a lateral displacement of up to 0.0550 mm, and the x direction, the k factor, that is the p divided by 1/2 gamma h square. To start with, it is close to 2, because we applied some lateral deformation. This is not exactly 2, but so it is close to 1.98. It has reduced to 1.8, 1.63, and so on. And then finally, at some point, it has reached a point 274. And for a friction angle of 35 degrees, the K should be 0.2714. So if you deform a little more, we might reach the limit state, active limit state. But in this particular case, because the K0 is very high, you require very large deformation. Okay. So by doing this, we can save some important data, and then we can import this into an Excel file. Let me show you how to do that. These columns can be directly transferred into the Excel file. Not sure whether we have Excel here. Well, I think the Excel file is not, Excel program is not here. What we do is we can take this and separate all the columns by tabs. There is a tab in between these two columns, so you can use the paste special and then use the tab as the separator between the columns, and then the program, the Excel will be able to easily download this into the Excel, and then you can select the columns and plot graphs similar to what I have shown here. So all these graphs, they are plotted by importing the data from the finite element program into this into the Excel program, and then after that we can manipulate in the usual manner that we do, and we can plot the graphs. Okay. So, I hope you appreciate how easy it is to generate limit solutions, and in the next class I am going to demonstrate some more cases, like the case of eccentrically loaded footing and so on. And there is another program called as a preprocessor that will let you generate the meshes, and I may not be able to demonstrate, but I will give you the instructions on how to generate the data files, so that you do not need to go through the user manual and then enter the data manually. So, that I will do that through some instructions, and you just follow the instructions, and it is very easy. All these programs are very easy to run. Okay. And if you have any doubts, or if you encounter any problems in the process, you send an email to this address profkrg@gmail.com, then I will respond back to you. So, thank you very much.